Hello Year 9s, I hope you're all having a captivating Saturday. Here we are to advance our knowledge of linear relations. Today we are going to look at an application of linear relations called direct proportion. So direct proportion is all of these situations where there's a constant rate of change. And that's best shown by examples. Average speed. Let's say you're travelling along at 80 kilometres per hour constantly. You'll gradually travel further and further in a straight line relationship. So here would be time and here would be distance. Or if you've got a pipe that water is flowing through, it might put 3,000 litres per every hour. Again, it'll be a direct relationship. As time goes on, the amount of water that's gone through that pipe, 3,000 each hour, it'll go up in a straight line. So it represents particular types of relationships. There are technical ways that I can explain that, and the text very much goes there. This is a general case. You have your X and Y axis. Starts at 0, nothing's happened at time 0. You've travelled no distance at time 0. There's been no water through that pipe at time 0. So all these direct proportion cases go through 0, 0. What's the special name for that location in the middle there? Do you remember? We call it the origin. So direct proportion cases go through the origin. You may remember our rule for linear relations. Y equals mx plus c. But the y-intercept, c, where's it always cutting the y-axis? At 0, right? So c in these direct proportion cases is always 0. So guess what? We could rub out the plus c because it's always 0. So the general rule looks a little like this. You may have some different variable labels in there. And of course you need to remember what m is. What's m? It's our friend gradient, right? And we've gone into how we are meant to calculate gradient previously. Now, this week, we're meant to get through quite a bit of content. So what I'm going to try to do is not make any individual video particularly long. So today what I'm going to do is I've decided I'm going to do an example of modelling using direct proportion, one that's different to the text. You'll have different examples if you want to look in the text. And we'll just run with that for today, and then you should be comfortable with this section because this leads into its exercise 4E that we're leading into with this content. All right, I want to talk about my car. I like my car. Not the best thing for the environment in the world, and I definitely am not allowed to travel anywhere at the moment, as with everyone else, so I'm not actually doing this, I'm just dreaming of it. Driving long distance, my car used 40.32 litres, travelling 560 kilometres. And that might sound like a bit of useless information for you, but being extension, I've skipped a bit of explanation in the questions. Sometimes these questions lead you on through the process, and I've gone straight into it. I've gone, find a rule. Find a rule of how much fuel is used based on the distance travelled. So think about that in terms of your dependent and independent variables, right? Diagrams are often a very good idea with these questions, particularly if you want to make sure you're getting an understanding of it. Now, does fuel depend on distance or distance depend on fuel? I'd argue that definitely the amount of fuel depends on the distance, right? So fuel is the dependent variable. Dependent variable's on the y-axis. Independent is on the x-axis. So here is our distance. I'm going to have to sneeze. And here is the amount of fuel used in litres. Now this definitely is direct proportion. It's definitely going to start at 0 because how much fuel have I used if I've travelled 0 kilometres? 0 litres, right? It's starting at the origin, and I'm assuming, and that's not a safe assumption, but we're going to assume a constant use of fuel at a certain rate. So it tells us that when we've travelled 560 kilometres, it's going to have used 40.32 litres. So we're assuming a straight line relationship that ends up here when x, the distance is 560, the amount used is 40.32. Right? Now to create a model here, remember our general rule, y equals mx. Well, in this case, instead of y, we've got f representing, actually I probably shouldn't call it f. F means function later on in mathematical methods. So what's another letter we might use there for the amount of, I might use L. That's annoying, isn't it? I'm going to change it to L because I don't want to use F, because F has a particular meaning in mathematics. So we're going to get L instead of Y and D instead of X. But fundamentally, we've still got to work out what M is, don't we? All right, to make a model linking the amount of fuel used to the distance, we need to work out what the gradient is. So I'm hoping from previous lessons you might remember gradient is worked out by y2 take away y1 over x2 take x1. That simply requires 2 points. We actually have 2 points. We have that one there. What's the other point? 0, 0. Right? We also have 0, 0. So if we put some labels on that, there's x1, y1, x2, y2. I have to admit I've done that partly because I know that, no, I'm actually going to do it the other way around. Because if those two values there are 0, it's going to make my calculations really easy. All right, so that can be the second point, x2, y2. That can be the first point, x1, y1. All we're going to get is it's going to be 40.32 over 560. You can leave things as a fraction if you want. I will put it in the calculator though. 40.32 divided by 560. Oh, it comes out to a reasonable looking fraction, so that's not too bad anyway. So 0.072. And therefore our model, the amount of litres used, the fuel in litres, is going to be 0.072 multiplied by the distance, d. So there we go. We've got a rule linking the amount of fuel used to the distance travelled. Now the important bits of what I just did in the modelling there is you really have to define what's your independent variable, what's your dependent variable. Independent is what's in place of x, dependent is what is in place of y. Then you can work out the rules simply by calculating the gradient. You calculate the gradient the same way as we've done in previous lessons. You use your y2 take y1 over x2 take x1. At the end, make sure to actually state what your model is. A lot of people will do this wonderful work and find out the gradient, but in the end, it's the model you want. You want the model linking the distance to the fuel usage. Now, straight up now, what we're going to do is a couple of examples using the rule we've just created. All right. Now, if you did this properly, that was just a sketch, but if you were asked to properly draw it, I'd expect you to use your ruler and a proper scale and all that sort of thing. Do it properly. All right. So here we go. By the way, the text does the gradient calculation slightly differently. I've just made sure to refer to doing it the same way as we've done in the past. I'm going to take off the first bit of this lesson now. Whole point of what I'm about to do, we're about to use that to answer a couple of questions. Right. Now I actually need to do something quickly to make the question. Okay. How many litres used? All right, so here we go. The fuel warning light came on at 680 kilometres. How much fuel has been used? That can be the first question. All right, so in here we're given a distance. In our model, the distance is represented by the letter D. Remember, D was distance. Distance D. So we're given D and we're asked how much fuel was used. So we're being asked for L. So to work this out, we'd write our model. L equals 0.072 D. And we put our value of D in it, 680. Turn to our calculator, 0.072 times 680. It'll tell us that 48.96 litres has been used. Right. 48.96 litres. Which is interesting because you might turn around and go, but hang on, I've got a 65 litre fuel tank. So you realise that in theory, you still have a lot of fuel left. You shouldn't run the fuel too low for probably fairly obvious reasons, but you know, it's interesting to know when your fuel light turns on compared to your fuel capacity. All right, I'll do a second quick question here and that'll be it for this video. The second one will be, I have a 70 litre fuel tank. How far can I theoretically travel on one tank of fuel? Right, theoretically travel on one tank of fuel. I realised the hard way once that theoretically what your fuel tank capacity is and what it actually is can be slightly different. I discovered that a 70 litre fuel tank I had once was actually closer to 67.5. I found that out the hard way. Anyway, so 70 litres. This time we're being given L. We're being given the amount of fuel used, 70 litres. So this time we're being given L, and we want to know how far we can travel. So we want to know D. So again, we state our rule. L is 0.072 D. We're given L, which is 70, so 70 equals 0.072 D. What do I do to both sides to get D by itself? We're going to divide by 0.072 from both sides. In effect, I need to know 70 divided by 0.072. Put it in your calculator. And it's telling me the distance I can travel is about 972.2 kilometres on the one tank. So you would answer fully, I just lack space on the board. So approximately 972 kilometres is how far I could travel on one tank. In the same way, over here, you'd say approximately 48 litres has been used, 49 litres. So with word questions, we are an extension class. A worded explanation at the end saying what on earth you actually got and what it means is a good idea. And often there's a mark just saying what on earth it means in those A-level questions at the end. So it's a very good idea to get in the habit of explaining what on earth you've actually got there. Right, that's today, guys. Direct proportion. It can represent a whole heap of situations involving rates where there's a constant rate, where I'm walking at 5 kilometres per hour, I'm running at 8 kilometres per hour, I'm cycling at 15 kilometres per hour. There's all sorts of ones like that. Fluid, situations of water and substances going through a pipe, even a petrol pump, it'd have a certain amount coming out of it every second. Anything that involves a constant rate, and I'm sure there's many other examples we could use here, but they're just the ones that come to mind quickly, as I'm not the most creative human in the world. All right, go forth and enjoy 4E. See yous.